Our today's topic is transformer. Transformer is a device which is used to transform electrical power from one voltage and current level to the other. We use transformer for getting our desired voltage. It is a device which is used to alter the alternating voltages. Working principle of transformer. The transformer is based on two principles: electromagnetism. An electric current can produce a magnetic field. And second principle is mutual induction. An EMF is induced in one coil by changing the current in neighboring coil. You are aware of both the principles, and in transformer we use these two principles. This is the structure of transformer. It consists of primary coil. This coil is known as primary coil. A coil with number of turns Np. Number of turns of primary coil are represented by N sub P, P for primary coil, connected to input electrical supply. Primary coil is connected to input electrical supply. Secondary coil. A coil with number of turns N sub S connected to the output. This coil is known as secondary coil, and number of turns of secondary coil are represented by N sub S, S for secondary coil. And secondary coil is connected with the output. Iron core. A laminated soft iron core on which two coils are wounded. These two coils, primary coil and secondary coil, these two coils are wounded on this iron core. Working of transformer. Current passing through the primary coil creates a magnetic field. Here in primary coil, current passing through this primary coil creates magnetic field, as we have discussed it many times that when charges flow, due to flow of charges, due to current, there must be a magnetic field around that conductor. The primary and secondary coils are wrapped around a core of high magnetic permeability such as iron, so that most of the magnetic flux passes through both the primary and secondary coil is same. Here we have primary coil, here we have secondary coil. Both are wrapped around a iron core that has high magnetic permeability. Due to high magnetic permeability of this iron core, most of the flux passing through the secondary coil is same as the primary coil. So flux through primary coil is almost same as the flux through secondary coil due to the high permeability of this iron core on which both the coils are wrapped. The changing magnetic flux through primary coil gives rise to an induced EMF Vs in the secondary coil. We know that here input is AC supply, and due to AC supply, polarity of current is changing, and due to that magnetic flux through primary coil is changing, and magnetic flux passing through primary coil is same as the magnetic flux passing through the secondary coil. And due to change in flux, magnetic flux through primary coil, the EMF is induced in secondary coil, as we have discussed this in mutual induction, and this EMF is induced in the secondary coil due to the change in flux in primary coil. And this induced EMF is known as V sub S, S for secondary coil. The voltage induced across the secondary coil is given by Faraday's law. So induced voltage in this secondary coil can be given by Faraday's law, that is induced EMF in secondary coil, that is V sub S, is equals to N sub S, number of turns of secondary coil, into d phi divided by dt, rate of change of magnetic flux. We have discussed this formula in Faraday's law. Let's say it equation number I. The voltage across the primary coil is given by V sub P. P represents primary coil voltage of primary coil, that is equals to N sub P. P represents primary coil, number of turns of primary coil, into d phi divided by dt, rate of change of magnetic flux. Let's say it equation number 2. Dividing equation 1 by equation 2, we have Vs divided by Vp is equals to Ns divided by Np. Voltage of secondary coil divided by induced voltage of primary coil is equals to number of turns of secondary coil divided by number of turns of primary coil. This is called transformer equation, where Vs is equals to voltage in secondary coil, Vp is equals to voltage in primary coil, Ns is equals to number of turns in secondary coil, Np is equals to number of turns in primary coil. Types of transformers. There are two types of transformers. Step-up transformer. Such type of transformer in which secondary voltage is greater than primary voltage is called step-up transformer. If number of turns of secondary coil is greater than number of turns of primary coil, then voltage secondary coil is greater than voltage in primary coil, and transformer is step-up transformer. We use step-up transformer where we need more voltage than provided voltage, more output voltage than input voltage. So there we can increase the number of turns of secondary coil and we can get the greater output voltage. Step down transformer. Such type of transformer in which secondary voltage is smaller than primary voltage is called step down transformer. We use step down transformer where we need less amount of voltage as compared to input voltage. So when we need in output less voltage, so we can decrease the number of turns of coil of number of turns of secondary coil. So if number of turns of secondary coil is less than number of turns of primary coil, then secondary coil voltage will be less than primary coil voltage, and transformer is step down transformer. So in output we'll get less voltage as compared to input. Ideal transformer, the amount of energy cannot be stepped up or stepped down. An ideal transformer is a transformer whose efficiency is 100%. In case of induction coil, the energy obtained from the secondary coil put into the primary coil to become 100% efficient. So output power is equals to input power. In that case, we have output power that is equals to V into I, voltage of secondary coil Vs into current of secondary coil Is, that is equals to input power voltage of primary coil into current of primary coil, and we get Vs divided by Vp is equals to Ip divided by Is. The above equation shows that if the voltage is stepped up, the current is stepped down and vice versa. So if we step up voltage, then current will be stepped down. Energy losses in transformer. There may be some energy losses in transformer. It is not 100% efficient device, although it comes in the range of 90% efficient devices, but there may be some energy losses in transformer. It may be due to flux leakage. When flux due to the primary coil passes through the secondary coil, some flux is leaked due to the poor design of the core or the air gaps in the core. We know that flux due to primary coil passes through the secondary coil, or there may not be complete transfer of flux through secondary coil due to the primary coil. It may be due to the poor design of the core or maybe due to the air gaps in the core. So it can be reduced by winding the primary and secondary coils one over the other. So we can reduce this flux leakage by winding primary and secondary coils one over the other. Another reason of energy losses is resistance of windings. The wire used for the windings has some resistance, and so energy is lost due to the heat produced in the wire. This can be minimized by using thick wires. So by using thick wires we can minimize the resistance, and that will be the reduction of heat produced in the wire. So by this we can minimize the energy losses in transformer. Another reason for energy losses in transformer is eddy currents. A transformer has an iron core to concentrate the magnetic field to achieve the maximum possible inductive coupling between the primary and secondary coils. As the changing flux intersects the core, eddy currents are induced in the coil. We use iron core to concentrate the magnetic field, and we know that flux is changing, and due to change in flux in the core, eddy currents are produced, and due to that, heating effect is observed in the core of iron that may cause the energy loss in transformer. So to minimize the eddy currents, we can use the laminated iron, in which sheets of iron are separated by thin insulating layers. Eddy currents can be minimized by laminating the iron core with insulation layer. Another cause of energy losses in transformer is hysteresis. The magnetization of the core is repeatedly reversed by the alternating magnetic field. Due to the alternating magnetic field, magnetization of core is reversed. The resulting expenditure of energy in the core appears as heat and is kept to a minimum by using a magnetic material which has a low hysteresis loss. So we can minimize this effect by using a magnetic material having low hysteresis loss.